Hi, I'm Patrick Reagan. Welcome to TCP/IP, Part 12, More on IP version 6. During this video, we continue our discussions about IP version 6, which will focus on some backend technologies used in IP version 6, including Neighbor Discovery Protocol, or NDP, ICMP version 6, DHCP version 6, Stateless Address Auto-Configuration, or SLAAC, and various IP version 4 to IP version 6 transition methods. If you liked my video, don't forget to click the like button, and if you have not already, subscribe to the Pat Has Your Back channel. As with most of my training videos, there are practice questions toward the end of the video. Neighbor Discovery Protocol, or NDP, is a protocol in the Internet Protocol Suite used with IP version 6. It operates at the link layer of the OSI model, layer 2, and is responsible for several functions crucial to the operation of IP version 6. Key functions of NDP include router discovery, which allows hosts to discover the presence and availability of routers on the local link. As the name implies, it enables the discovery of IP version 6 neighbors by performing functions similar to ARP in the IP version 4 that helps discover MAC addresses of other devices on the same local network segment, which allows you to map IP version 6 addresses to MAC addresses. Prefix discovery allows hosts to learn the network prefixes assigned to a local link. Parameter discovery allows hosts to learn link parameters such as the maximum transmission unit, or MTU. Address auto-configuration supports stateless and stateful address auto-configuration for IP version 6 addresses. Neighbor unreachable detection, or NUD, determines if a neighbor is reachable or not, ensuring valid reachability. Duplicate address detection, or DAD, ensures that no duplicate IP addresses exist on the network. Redirect function informs hosts of a better first hop router for reaching a destination. Instead of using broadcast, it operates using multicast over ICMP version 6. In IP version 6, router solicitation, or RS, and router advertisement, or RA, are critical components of the Neighbor Discovery Protocol, which replaces parts of IP version 4's ARP and ICMP functionality. These two message types are used primarily for stateless address auto-configuration and discovery routers on the local link. Router solicitation, or RS, is sent by IP version 6 hosts, typically during startup, uses all routers' multicast address to prompt routers on the local link to immediately send a router advertisement rather than waiting for the periodic RA interval. This speeds up the process of obtaining network configuration such as default gateway and the network prefix. Router advertisement, or RA, is sent by IP version 6 routers periodically or in response to RS to learn prefixes, determines whether to use SLAAC, DHCP version 6, or both, and get default gateway. It's necessary for auto-configuration of IP version 6 addresses. Internet Control Message Protocol, for IP version 6, is the IP version 6 version of ICMP used in IP version 4. It's a critical Layer 3 protocol defined in RFC 4443 that enables diagnostic and error reporting capabilities in IP version 6 networks and supports advanced features such as Neighbor Discovery Protocol and Multicast Listener Discovery, or MLD. Unlike in IP version 4, where ARP, ICMP, and IGMP were separate protocols, IP version 6 consolidates multiple network layer functions under ICMP version 6. Error messaging reports unreachable destinations, packet time exceeded, and parameter issues. Informational messaging includes echo request and echo reply for tools like Ping 6. Neighbor Discovery, or NDP, provides address resolution, router discovery, prefix discovery, and so forth. Multicast Listener Discovery manages multicast group memberships, which replaces IGMP and IP version 6. Path MTU Discovery helps determine the largest packet size the path can support without fragmentation. Redirect messages informs the host of a better first hop router on the same link. In IP version 6, Router Advertisement Guard, or RA Guard, is a security feature used to protect the network from malicious or rogue router advertisement messages, which are part of the ICMP version 6 neighbor discovery protocol. It's essential for dual stack and SLAAC-based networks to prevent IP version 6 network disruptions and mitigate rogue RA attacks. Without protection, any host on the network can send fake RA messages to redirect traffic, creating a man-in-the-middle attack, disrupt IP version 6 addresses by providing bogus prefixes or default routes, break connectivity, especially in dual-stack networks where rogue RAs can override legitimate IP version 6 or cause preferring broken IP version 6 paths. RA Guard is a Layer 2 security feature on switches that inspects RA packets, blocks unauthorized or rogue RA messages from being sent from host ports, and allows RA messages only from trusted interfaces, which is usually uplinks to legitimate routers. It works by enabling RA Guard on access points or user-facing, configure uplink or router-facing ports as trusted, and the switch inspects IP version 6 packets with ICMP version 6 type 134 and drops unauthorized ones. In IP version 6, the DHCP server is used for address assignment and configuration of other network settings, just like in IP version 4, but with some differences depending on the mode in use. There are two main forms of DHCP for IP version 6 or DHCP version 6 modes. Stateless DHCP version 6 provides only additional information like DNS and domain search list, while the IP address is assigned via SLAAC. Essentially, it's used to a SLAAC, whereas router advertisement provides the address and DHCP gives it the extras. Stateful DHCP version 6 is similar to IP version 4 DHCP, but provides full IP address assignments, lease tracking, and config options such as DNS and domain search list, which is useful in managed networks that require tracking of leases and host information. Stateless Address Auto-Configuration, or SLAAC, is a method for IP version 6 clients to automatically obtain IP addresses and other network configuration information without manual configuration or a DHCP server. It's also known as IP version 6 auto-configuration. It determines the IP prefix using neighbor discovery protocol, router solicitation, and router advertisement. Instead of using DHCP server, it relies on router advertisement sent by routers. The host generates the address based on its own interface identifier, usually based on the MAC address or a randomly generated number, and combines it with the router's advertised prefix to form a full IP version 6 address. No separate server keeping the state, which means no tracking of IP or MAC addresses and lease times don't exist. By default, SLAAC can use the host MAC address or EUI64 format, which is a privacy-invasive privacy extension. If you're concerned with privacy tracking, you can use a stable randomized identifier, again without any centralized tracking. It uses duplicate address detection, or DAD, to ensure that no duplicate IP addresses exist on the network. Instead of DHCP-like lease times, SLAAC uses lifetimes advertised in router advertisements. Types of lifetime include a valid lifetime on how long the address is valid, which is usable for communications, and preferred lifetime, which is how long the address should be used as preferred before deprecation. These lifetimes are included in the RA along with each advertised prefix. Once the preferred lifetime expires, the address is considered deprecated. It is still valid, but should not be used for new connections. After the valid lifetime expires, the address is invalid and must be removed. Extended Unique Identifier 64-bit, or EUI64, is a method for generating a unique 64-bit interface identifier, or IID, for IP version 6 addresses by using the device's MAC address, which is 48 bits long, to create a 64-bit IID that can be used as a host portion of a unicast network IP version 6 address or linked local address when stateless auto-configuration is used. This method helps to avoid manual configuration in DHCP and IP version 6 environments. Note, while the EUI64 format was initially adopted for its ability to provide unique interface identifiers, it has been deprecated in some contexts due to privacy concerns. Embedding the MAC address into IPv6 address can expose device information and allow for tracking across networks. As a result, modern systems often use privacy extensions or stable privacy addresses that generate random interface identifiers to mitigate these concerns. To change the 48-bit MAC address to 64-bit address, you need to split the MAC address into two 3-byte or 24-bit halves, put FFFE in the middle, and invert the 7th bit. An example is shown on the screen. You have the MAC address, which is divided into two halves. You then put the FFFE in the middle of the two halves. You then invert the 7th bit. Inverting the bit ensures that the system can distinguish between burned-in and locally generated interfaces. Cisco has created a cheat sheet that shows you how to change the values quickly without doing any binary conversions. For example, if the second hex digit is a 0, change it to a 2. If the second hex digit is a 2, change it to a 0. IPv6 native mode uses only IPv6, offering higher performance and reduced overhead, but requiring devices to fully support IPv6. IPv6 transition methods are crucial for ensuring interoperability between the existing IPv4 infrastructure and the emerging IPv6 networks. It includes dual stack, which is the most preferred and best practice, tunneling technologies, which are declining but still appear in legacy and ISP environments, and translation techniques, which are ideal for IPv6 only networks reaching IPv4 resources. A dual stack routing, also known as dual stack networking, is a networking environment that supports the simultaneous use of both IPv4 and IPv6 addresses. This configuration enables devices to run IPv4 and IPv6 concurrently, resulting in a smoother transition from the older IPv4 to a more modern IPv6. While it provides seamless operations with native support for both protocols, it requires IPv4 and IPv6 routing infrastructure. Dual stack allows for a gradual and seamless transition to IPv6. Best practice today is to deploy dual stack where possible. Note, you can also load both IPv4 and IPv6 protocol stacks on the same computer. While the computer can have both IPv4 and IPv6 addresses, it doesn't mean both are used simultaneously for every network connection. A computer will typically use either IPv4 or IPv6 for a particular connection, depending on the destination's protocol support and configuration. The protocol stacks are typically run separate from each other. Tunneling technologies are used to encapsulate IPv6 traffic over existing IPv4 infrastructure. Tunneling methods are declining, but ISATAP, GRE, and 6PE, 6VPE still exist in legacy and ISP environments. 6-4 is used with networks that only have IPv4 connectivity by assigning a specific IPv6 address space to each 6-4 site, and where the IP version address is embedded in the IPv6 address. IPv6 packets are encapsulated with IPv4 packets for transmission across the IPv4 address. 6-4 relies on relay server or boundary router to handle the encapsulation and routing between the IPv4 and IPv6 networks. 6-4 is deprecated and rarely used today. Teredo is designed to provide IPv6 connectivity to nodes that are located behind IPv4 NAT devices by encapsulating IPv6 traffic with IPv4 UDP packets, enabling it to travel through firewalls and NAT devices. The clients encapsulate IPv6 packets in UDP, send them to a Teredo server, and the server forwards them to the destination. Teredo is deprecated. Intra-site Automatic Tunnel Addressing Protocol, or ISATAP, is a tunneling mechanism used to allow IPv6 traffic to be carried over an IPv4 network by creating a virtual IPv6 network on top of an existing IPv4 infrastructure, which allows devices on an IPv4 network to communicate using IPv6 protocols, even though they don't have native IPv6 support. It is also deprecated. Generic Routing Encapsulation, or GRE, is a generic tunnel that can encapsulate a wide variety of network layer protocols, including IPv6 over IPv4 transports. MPLS 6PE, 6VPE is used by ISPs to carry IPv6 over MPLS backbones. NAT64 is a mechanism that allows IPv6 only hosts to communicate with IPv4 only hosts by translating between IPv6 and IPv4 addresses and protocols. It translates IPv6 addresses to IP4 addresses and vice versa. It works with DNS64, which synthesizes quad A records from A records. This is particularly useful in scenarios where an organization is migrating to IPv6 but still needs to communicate with the existing IPv4 internet. These protocols and mechanisms are vital components of modern network infrastructures, facilitating smooth transitions and communication between different types of networks and addressing schemes. NAT64 works by starting with the IPv6 client, sends a request to an IPv6 address in a special format that's usually prefixed with the address of the NAT gateway, default well-known NAT64 prefix. DNS64 is a companion technology that synthesizes a quad A IPv6 record from an IPv4 A record. The destination server is IPv4 only. The NAT64 gateway receives the IPv6 packet, translates it into an IPv4 packet, modifying the headers, and forwards it to the IPv4 destination. Responses from the IPv4 server are translated back into IPv6 and returned to the client. In IPv6 DNS, quad A records are used to map host names to 128-bit IPv6 addresses instead of using A records for host records. Quad addresses are named because the name reflects a 32-bit record increased by 4 times or 128 bits for an IPv6 address. PTR records for IPv6 used for reverse lookup are under a different namespace. PTR records for IPv6 used for reverse lookup are under different namespace, as shown with the IPv4 reverse lookup and IPv6 reverse lookup zones. IPv6 uses IP6.ARPA, and each nibble or hex digit of the address is reversed and separated by dots. DNS64 is a domain name system extension used in IPv6 only networks to enable communications with IPv4 only servers. It works alongside NAT64 by generating synthetic IPv6 addresses from IPv4 DNS records. DNS64 is stateless. It doesn't track sessions or ports. It's used only for name resolution, not packet forwarding. It requires the corresponding NAT64 gateway to actually perform the IP port translation. When an IPv6 only queries for IPv6 records, but the destination has only an IPv4 record, the DNS server will look up the A record for the domain, synthesize a fake quad A record by embedding the IPv4 address into the IPv6 address using a NAT64 prefix, and returns the synthesized quad A record to the IPv6 client. The client then uses the IPv6 address to reach the IPv4 server via the NAT64 gateway. You want to assign addresses for IPv4 and IPv6. The DHCP server only supports IPv4. What can you use to assign IPv6 addresses without DHCP? Answer: SLAAC. Question: You're writing a script to periodically log the IPv6 and MAC addresses of all the devices on the network segment. Which of the following switch features was most likely to be used to assist with this task? Answer: Neighbor Discovery Protocol. Question: which of the following services provides the network information for the address when IPv6 is used with SLAAC addressing? Answer: routing advertisement. Question: you decided to use SLAAC in an extensive IPv6 deployment to alleviate IP address management. The devices were properly connected into the LAN, but auto-configuration of the IP address did not occur as expected. Which of the following should you verify? Answer: the network gateway is configured to send router advertisements. Question: which of the following services provides the network information for the address when IPv6 is used for SLAAC addressing? Answer: router advertisement. Question: you are switching to IPv6 and want to be able to use packet tracing software on the network to monitor traffic. You want to set up an IP addressing to include the MAC address of each machine that is connected. Which of the following should you implement? Choose two answers. Answer: EUI64 and SLAAC. Question: which of the following IPv6 transition methods requires all network devices to support IPv4 and IPv6? Answer: dual stack. Question: you want to address PCs on a subnet with IPv6 in addition to IPv4. The subnet currently uses the DHCP server that only supports IPv4. Which of the following should the technician use to assign IPv6 addresses automatically without DHCP? Answer: EUI64. For more information, visit the site. In summary, to facilitate simplified automatic addressing, the IPv6 subnet size has been standardized and fixed to 64 bits, and the MAC address is used to generate the host bits within the unicast network address. Neighbor Discovery Protocol, or NDP, is a protocol in the Internet Protocol Suite used with IPv6 that is responsible for router discovery, which allows hosts to discover the presence and availability of routers on the local link, and prefix discovery, which hosts use to learn the network prefixes assigned to a local link. Stateless Address Auto-Configuration, or SLAAC, is a method for IPv6 clients to automatically obtain IP addresses and other network configuration information without manual configuration or a DHCP server. A dual stack routing, also known as dual stack networking, which is the most preferred when transitioning from IPv4 to IPv6, is a networking environment that supports the simultaneous use of both IPv4 and IPv6 addresses. Thank you for watching this video. The next video will be TCP/IP Part 13, Understanding DNS. If you like this video, be sure to click the like button. If you have not already, subscribe to the Pat Has Your Back channel. Thank you.